Moment distribution method. One of the basic concepts in the moment distribution method is the moment needed to produce a rotation theta A for a beam with a pin or roller support with the other end fixed. This moment is derived and it is equal to 4EI over L times theta A. As a result of this moment, there will be corresponding carryover moment or reaction at the fixed support, and this is equal to 2EI over L theta A. It can be seen that the moment at the fixed support is 1/2 of the moment at the pin or roller support. This concept is very important in the moment distribution method. The bending stiffness factor or stiffness K is defined as the moment required to be applied at the hinge or roller support to produce a rotation equal to 1 radian. In the previous slide, the moment at the pin support is equal to 4EI times over L times theta. If theta is equal to 1 radian, then the moment is equal to 4EI over L. This is defined as the member stiffness. The relative stiffness factor is defined as the ratio of the moment of inertia divided by L. This parameter is usually used when the value of EI is constant for the whole structure. This can be shown in the following examples. The carryover factor is defined as the ratio of the moment induced at the fixed end to the moment at the hinge end. In our previous equations, the moment at the hinge support is equal to 4EI over L times theta, and the moment at the fixed support is 2EI over L times theta. Hence, the ratio of the moment at the fixed support to the hinge support is equal to 1/2. This is defined as the carryover factor. The distribution factor is defined as the ratio of the stiffness of the member divided by the stiffness at the joint. The derivation is shown as follows. If we have a frame consisting of members AB, BD, and BC, and we apply a moment that will produce a rotation at B equal to theta B. This moment will be resisted by the members as MBA, NBD, and NBC, and this can be shown in an equilibrium equation that the moment M minus MBA minus MBC minus MBD should be equal to 0. The moment of the members can be expressed in terms of the previous equation of 4EI over L times theta. And as we defined earlier, 4EI over L is simply the stiffness of each member, in this case KBA, KBC, and KBD, using the corresponding values for E, I, and L per member. The rotation theta B can be derived as M divided by the summation of the K which is called the joint stiffness. If we are interested to determine the moment for a specific member, let's say BA, it is simply defined as the stiffness of the member multiplied by theta B. Substituting the value of theta B there, we can now express the moment for BA is equal to the distribution factor for BA multiplied by the moment. The distribution factor is defined as the stiffness of member BA divided by the summation of the stiffnesses at that joint, which is defined as the joint stiffness. Similarly, for member BC, the moment is equal to the distribution factor, which is KBC, divided by summation of K. And NBD is defined as the stiff distribution factor times the moment, so KBD divided by summation of K. It can be shown, it is shown in these equations that the moment of the member is, the moment carried by the member is directly proportional to its stiffness, which means the larger the stiffness of the member, the larger will be the moment that it will carry at that, due to the bending moment M. The distribution factor is defined as the ratio of the stiffness of the member to the sum of the stiffnesses of all the members at the joint, as defined earlier. And in this example, the distribution factor for member 1 is just equal to the stiffness of member 1 divided by the sum of the stiffnesses of all the members connected to that joint, which is defined as our joint stiffness. This is called the joint stiffness. There is a special case when the joint is a wall or fixed support. The joint stiffness is equal to infinity because at the fixed support, rotation is equal to 0. Fixed end moments. One of the parameters used in the moment distribution method are the fixed end moments. So it's important that you remember the standard formulas for various types of loadings, such as concentrated load applied at the distance A and B from the left and the right, uniform distributed load, and other types of loadings. The moment distribution method can be summarized as a procedure consisting of the following steps. The first step is we lock all the joints such that there will be no rotation. To lock all the joints, we use the fixed end moments. Second, we release the joint so that rotation will occur. To release the joint, we determine the unbalanced moment at that joint due to the fixed end moments. Third step, we apply the distributed or a balancing moment, and this moment is applied opposite in direction to the unbalanced moment in step number 2. The balancing moment is distributed for each member depending on the distribution factor of that member. Step 4, when you apply a moment at the member, a carryover moment will be induced at the other end by applying the carryover factor, which is equal to 1/2. Steps 4 and 3 are repeated until several cycles or until the distributed moments become negligible or small. After step 5, we can now determine the end moments, which are the same moments we derived in the slope deflection method. The moment distribution procedure can be described by these figures. This is our actual structure, and in the actual structure, there is a uniform load, and as a result of this uniform load, there will be a rotation theta b. The first step in the moment distribution method is we fix all joints so that there will be no rotation at any joint. When you fix all joints, the fixed end moments will be developed. Next, at each joint, let's say joint B, there will be a clamping moment due to the fixed end moments of all the members connected to that joint. We apply a moment opposite in direction, like so, which is called the balancing moment. This balancing moment will be distributed to the members, say BA, BC, and BD, directly proportional to the distribution factor per member. When you apply the moments MBA, MBC, and MBD, a carryover moment factor will be developed at the other end, and these are called the carryover moments. The procedure is repeated until several cycles. These are video tutorials if you want to learn more about moment distribution method. These are some suggested links for tutorials, and if you want to automate the moment distribution method specifically for your problem set, you can watch this video. They're also available online resources in the internet. Thank you very much for your attention.